Hey everyone. Today, I want to talk about limits and continuity of complex valued functions. Now, before we get into that, we first need to define what a complex valued function is. And so, a complex function f is a map from a subset g of c to c. We write this notation, f from g to c, where g is the domain of f and c is the codomain of f. Each element z in g gets mapped to exactly one element called the image of z, denoted by f of z. And so what you'll notice here is that a complex valued function is basically the same thing as a real valued function, except it maps complex numbers to complex numbers rather than real numbers to real numbers. And so we can define complex valued functions the exact same way that we define real valued functions. So some examples of some complex valued functions might be f of z equals z, which is just the identity map, right? Because it maps z to itself. We might have f of z equals 1 over z, which is the map that maps complex numbers to their multiplicative inverses, and we can even define polynomials. So we can have f of z equals z squared plus z minus 3. And so these are all valid complex valued functions. Now, some other things that you could potentially do is maybe add in like an I here, right? Because we have that imaginary axis in the complex plane. Or you might even take like the conjugate of a complex number as well. So we can also do those things in complex valued functions. We can also construct complex valued functions using different representations of complex numbers. So instead of just saying something like f of z equals z, we can also write complex valued functions in terms of real and imaginary parts. So we could write a complex valued function that takes two inputs where x is the real part and y is the imaginary part. And we could write something like 2x squared minus 3iy. And this is also a completely valid complex valued function, right? Because you're still mapping a complex number to a complex number. You're simply mapping the real and imaginary parts separately rather than the entire complex number together in one piece. Great. Now, we can also construct a complex valued function using the polar representation. So we could write a complex valued function that takes in r, which is the modulus, and phi, which is the argument. And we could write it like 2r e to the I phi minus 7 or something like this. And this is also a valid way to write a complex valued function. Okay, we can now define the limit of a complex valued function. So suppose that f is a function from g to c and that z0 is an accumulation point of g. If w0 is a complex number such that for every epsilon greater than 0, we can find delta greater than 0, so that for all z and g satisfying that z is within delta distance of z0, we have that the image of z is within epsilon distance of w0, then w0 is the limit of f as z approaches z0. And so the notation we use to describe the limit is this notation down here. And so essentially what this definition is getting at is that for every epsilon greater than 0, which is determining some open disk around w0 of radius epsilon, we want there to be a delta, which determines some open disk of radius delta around z0, such that every point within the delta disk maps to a point within the epsilon disk. And so we want this to be the case for every single epsilon. So if we make epsilon, let's say, much smaller, let's say like this size, well, we want there to still exist a delta that determines some open disk around z0 so that every single point within the delta disk maps to some point within the epsilon disk. And so this is what this definition is getting at here. And so some of the nuance in this definition that we need to pay attention to is that z0 needs to be an accumulation point of g, because in this part of the definition here, where we're saying all of the points within delta distance of z0, well, in order for us to be guaranteed that there are points within delta distance of z0, z0 needs to be an accumulation point of g. So just remember that going forward, that we need z0 to be an accumulation point of g. All right, let's go ahead and go over an example. So I want to prove that the limit of z squared as z approaches I is -1. And so recall from the definition of the limit that what we want to do is, given epsilon greater than 0, we want to choose a delta greater than 0 such that the modulus of z minus z naught being between 0 and delta implies that the modulus of f of z minus w naught is less than epsilon. And so what is z naught in this context? Well, remember that z naught is the complex number that we're approaching in the domain. And so in this case, z naught is simply I. Now what about f of z? Well, this is just our function, which is z squared. So we'll replace f of z with z squared. And then what about w naught? Well, w naught is our supposed limit, which is -1. So we have z squared minus -1, which is just z squared plus 1. And so in this case, we want to prove that the modulus of z minus I being between 0 and delta implies that the modulus of z squared plus 1 is less than epsilon. So let's go ahead and do that with a proof. So let's go ahead and start off our proof here. And so the first thing I want to do is I want to factor out the modulus of z squared plus 1, which is equal to the modulus of z minus I times the modulus of z plus I. And so recall that we want to show that the modulus of z minus I being between 0 and delta implies that the modulus of z squared plus 1 is less than epsilon. And so we're going to go ahead and assume that the modulus of z minus I is less than delta, since this is the condition we care about. And so we have a modulus of z minus I right here. And so what we can do is we can bound this expression above by delta times the modulus of z plus I, because we're assuming that the modulus of z minus I is strictly less than delta. Okay, so from here, I want to say, suppose that delta is less than 1. And the reason that I'm going to suppose this is because that's going to allow us to bound the modulus of z plus I. Okay, so from here, I'm going to say that delta times the modulus of z plus I equals delta times the modulus of z minus I plus 2i, right? Because negative I plus 2i simply equals I, so these two expressions are equivalent. And so recall that the modulus of a sum or difference is equal to the sum or difference of moduluses. And so this is equal to delta times the modulus of z minus I plus the modulus of 2i. And this should be in parentheses here. Great. And so notice that the modulus of 2i is simply equal to 2. So let's go ahead and replace that. Okay. And so remember that we're assuming that the modulus of z minus I is between 0 and delta. So we can bound this expression above by 3 delta, right? Because we have 2 in here, and then we know that the modulus of z minus I is bounded above by delta, and delta is less than 1. So delta times the modulus of z minus I plus 2 must be less than 3 delta. Great. From here, let's choose delta to be less than the minimum of epsilon over 3 and 1. And so what this is going to allow us to do is, well, we know that if delta is less than 1, which is guaranteed by this inequality, then the modulus of z plus I is bounded above by 3, and this inequality holds here. And rather, the modulus of z squared plus 1 is less than 3 delta through this big chain of equalities and inequalities. And we also know that if delta is less than epsilon over 3, which is also guaranteed by this inequality, well, that gives us this. That gives us the modulus of z squared plus 1 is less than 3 delta is less than epsilon. And the reason for this is because we know that delta is less than epsilon over 3, and so multiplying by 3 on both sides, we get that 3 delta is less than epsilon, which is this inequality right here. And so we've just completed our proof. We've just found a delta for every epsilon such that the modulus of z minus I being between 0 and delta implies that the modulus of z squared plus 1 must be less than epsilon. And so we've proven that the limit of z squared as z approaches I equals -1. Okay, now I'd like to go over a theorem that's going to allow us to prove that a particular limit does not exist. So suppose that f is a function from g to c, and that the limit of f of z as z approaches z naught is w naught. Suppose that g tilde is a subset of g, and z naught is an accumulation point of g tilde. If f tilde is the restriction of f to g tilde, then the limit of f tilde of z as z approaches z naught exists and has value w naught. And so to illustrate what this theorem is getting at, let's draw out an example. Let's say I've got the complex plane here, and I have some function f from c to c. And let's say in this example, I want to find the limit of f as z approaches 0. Well, what this theorem says is that regardless of how we restrict our domain, so let's say we restrict our domain to this line through the origin here. And notice that this is indeed a restriction of the domain because any set of points in C is a subset of C. And so regardless of how we restrict our domain, we could even restrict it to some weird curve like this. Well, the limit along any of these restrictions to the same point should have the same limit. And this is because each of these restrictions is a subset of C. So you can think of these restrictions sort of as the G tilde from the theorem. And so this theorem says that if all of our assumptions up here hold, then the limits along each of these restrictions should be the same. And so if they're not the same, one of our assumptions must have been incorrect. So what assumptions did we make? Well, the first assumption we made is that the limit of f of z as z approaches z naught exists and has some value w naught. So this assumption could be incorrect. Now, what other assumptions did we make? Well, we also supposed that our g tilde was a subset of g. And so each of these restrictions here, this line and this weird squiggly line, are indeed subsets of our domain C. So in this example, that condition is not violated. So that cannot be the assumption that's false. And so the last thing we assumed was that z naught was an accumulation point of our g tilde. And so in our example, each of these restrictions contains the point z naught and a bunch of points leading up to z naught. And so in this case, z naught, or 0 in this case, is an accumulation point of each of our g tildes. So if the limits along each of these restrictions disagrees, then the only assumption that could be false is that the limit of f of z as z approaches z naught exists. And so this is the strategy that we're going to use to prove that a particular limit does not exist. Okay, let's now prove that the limit of z conjugate over z as z approaches 0 does not exist. And so remember that our strategy is going to be to show that depending on the way we restrict the way we approach 0, different restrictions leads to different limits. So let's first start by letting z be a real number. So basically what we're saying here is that we're approaching 0 along the real axis. Great. Then the limit as z approaches 0 of z conjugate over z equals the limit as x approaches 0 of x conjugate over x. And since x is a real number, the conjugate of x is itself. So this equals the limit as x approaches 0 of x over x, which simply equals 1. So this is our limit along the real axis. Now let's approach it along the imaginary axis. So let z equal iy, where y is a real number. Then the limit as z approaches 0 of z conjugate over z equals the limit as y approaches 0 of the conjugate of iy over iy. and the conjugate of iy is negative iy, so this equals the limit as y approaches 0 of negative iy over iy, which equals negative 1. And so when we approached 0 along the real axis, the limit was 1, but when we approached 0 along the imaginary axis, the limit was negative 1. And since the limits disagree on different restrictions, the limit does not exist according to the previous theorem. Okay, now let's go over some properties of the complex limit. So let f and g be complex functions with domain G, and let z0 be an accumulation point of G, and let c be a complex number. If the limit of f of z as z approaches z0 and the limit of g of z as z approaches z0 exist, then we have these properties that hold. The first property is that the limit of the sum of two functions is equal to the sum of the limits of the two functions. And we also have this other rule sort of baked into this rule, which is that we can pull constants out of the limit, right? Because we have this c times g of z within the limit, and we pulled the c out of the limit here. Great, so that's property A. Property B is simply that the limit of the product of two functions equals the product of the limits of the two functions. And then finally, property C says that the limit of the quotient of two functions equals the quotient of the limits of the two functions. And it's important to note that with property C, the limit of g of z as z approaches z0 cannot equal 0 because we cannot divide by 0. Alright, just to get a little bit of proof writing practice in, let's go ahead and do a proof of property A, which remember said that the limit as z approaches z0 of f of z plus c g of z equals the limit as z approaches z0 of f of z plus c times the limit as z approaches z0 of g of z. And so recall back to the definition of a limit that this right-hand side, which is our supposed limit, is our w0 in this context. And so ultimately what we want to show through this proof is that given any epsilon greater than 0, we would like to choose delta greater than 0 such that the modulus of z minus z0 being between 0 and delta implies that the modulus of the image of z, which in this case is f of z plus cg of z, so I'll write that down, we have f of z plus cg of z, which is the image of z, minus w0, which recall is this entire right-hand side, and to make things a little bit shorter, we'll define the limit of f of z to be L and the limit of g of z to be M. And so we want the modulus of f of z plus cg of z minus L plus cm to be less than epsilon. So this is ultimately what we're trying to show through our proof here. Okay, let's go ahead and actually do the proof now. Let's go ahead and erase all this here. Okay, so the first thing we want to do is start by assuming that c does not equal 0. And the reason we want to assume that c does not equal 0 is because in the case that c does equal 0, the proof becomes trivially true, because the proof then becomes that the limit of f of z equals the limit of f of z, since the c times g of z terms go away since c is 0, and so that's trivially true, and we don't care about that situation. We care about the situation that is not trivial, which is the case that c does not equal 0. Great. So to make things a little bit simpler, let's let L equal the limit as z approaches z0 of f of z, and let's let M equal the limit as z approaches z0 of g of z. And so based on the definition of the limit, then we know that given epsilon greater than 0, we can find delta 1 and delta 2 greater than 0. And the reason why we have delta 1 and delta 2 here is because delta 1 is associated with the limit of f of z, and delta 2 is associated with the limit of g of z. These are two different values for two different limits. And so we can find delta 1 and delta 2 greater than 0 such that two conditions hold. And so the first condition is that the modulus of z minus z naught being between 0 and delta 1 implies that the modulus of f of z minus L, which is the limit of f of z as z approaches z naught, is less than epsilon over 2. And so notice that we're using epsilon over 2 here instead of epsilon. And the reason we're doing this is to be able to make things easier a little bit later in the proof. But the reason we're able to do this at all is because epsilon over 2 is still guaranteed to be a positive real number. And so remember that based on the definition of the limit, we're able to find a delta for any positive real number. So we can substitute any sort of modification on epsilon in here, or even a term that isn't even based on epsilon, so long as it's a positive real number and this condition still holds. And so we can say something similar for the g of z case. We can say the modulus of z minus z naught being between 0 and delta 2 implies that the modulus of g of z minus m is less than epsilon over 2 times the modulus of c, which is also guaranteed to be a positive real number. Let's make a little bit more room for our proof here. And so remember that the overall goal here is to choose a general delta that works for f of z plus c g of z. And so that's what we're about to do next. Let's get rid of all this stuff. All right, so what we want to say here is then choosing delta to equal the minimum of delta 1 and delta 2. And the reason that we're choosing delta to be the minimum of delta 1 and delta 2 is so that both of the previous conditions in the proof hold, right? Because if delta is greater than delta 1, then that condition with delta 1 doesn't hold, and the same thing for delta 2. So we need delta to be the minimum of these two so that both conditions are guaranteed to hold. And so choosing delta to be the minimum of delta 1 and delta 2, we infer that the modulus of z minus z naught being between 0 and delta implies that the modulus of f of z plus c g of z minus L plus cm, and notice that this is getting pretty close to what we want here, is less than or equal to the modulus of f of z minus L, kind of messed up the notation here, z closing parenthesis minus L plus the modulus of c times the modulus of g of z minus m. And so the reason that this inequality holds is that we actually use the triangle inequality. And so all you have to do to get out this right-hand expression here is rearrange the terms on the left-hand side and then use the triangle inequality. And so I'll let you figure out that little detail. And so the next thing I want to do is I want to substitute in something for the modulus of f of z minus L. Now, based on one of the previous conditions, the condition associated with delta 1, we can assume that the modulus of f of z minus L is strictly less than epsilon over 2. And so let's substitute that in. We know that this expression must be strictly less than epsilon over 2 plus the modulus of c times the modulus of g of z minus m. And so we can also replace modulus of g of z minus m with epsilon over 2 times the modulus of c, based on the condition associated with delta 2. And so substituting that in, we get epsilon over 2 plus modulus of c times epsilon over 2 times the modulus of c. The modulus of c's cancel out, and we're left with epsilon over 2 plus epsilon over 2, which is equal to epsilon. And so this is precisely what we were trying to show, is that the modulus of f of z plus c g of z minus L plus cm is strictly less than epsilon for our choice of delta. And so we have finished the proof. All right, next, let's talk about continuity. So suppose that f is a function from g to c. If z0 is in g, and either z0 is an isolated point of g, or the limit of f of z as z approaches z0 equals f of z0, then f is continuous at z0. F is continuous on a subset of G E if f is continuous at every point z in E. And so this is a really nice and simple definition that's made simple by the concept of the limit. However, generally speaking, when doing proofs involving continuity, you want to use an alternative definition involving epsilons and deltas. So let's go through that alternative definition. All right, so here's the epsilon delta definition of continuity. So suppose that f is a function from g to c and z0 is in g. Then f is continuous at z0 if for all epsilon greater than 0, there exists delta greater than 0 such that the modulus of f of z minus f of z0 is less than epsilon for all z and g satisfying that the modulus of z minus z0 is less than delta. And so this is very similar to the definition of the limit. So essentially what's going on here is we want that for all epsilon greater than 0, which determines some open disk of radius epsilon around f of z0, we want there to exist a delta determining some open disk of radius delta around z0 such that every point within the open delta disk around z0 maps to a point within the open epsilon disk around f of z0. And so this is the epsilon delta definition of continuity. All right, just to go over a quick example, recall that from earlier in the video, we showed that the limit as z approached I of z squared equaled -1. And so notice what happens when we plug in I into our function. So if we plug in I in for z here, we'll say that f of z equals z squared in this case. Well, we get I squared, which equals -1. And so since the limit of our function z squared as z approaches I is -1, and f of I is also -1, well, that means that our function f of z equals z squared is continuous at the point I. And so this is using the first definition of continuity that we went over, which is that if the limit of f of z as z approaches z0 equals f of z0, then f of z is continuous at z0. And so since we already have this limit figured out for us, we can use that simple definition to figure out that f of z is continuous at the point I. So that's just a quick example of continuity. Next, I want to go through the definitions of two other important concepts. So the image of the function g from big G to c is the set of g of z's such that z is in g. And so essentially the image of a function is the set of the images of all the individual points within the domain. And so if the image of g is contained in the domain of another function f from h to c, we define the composition f composed with g from big G to c through f composed with g of z is defined to be f of g of z. All right, now I'd like to talk about a theorem that gives us a nice property about the limits of compositions of functions. So let g be a function from big G to c with image contained in h, and let f be a function from h to c. Suppose that z0 is an accumulation point of g, that the limit of g of z as z approaches z0 is w0, which is contained in h, and f is continuous at w0. Then the limit of f of g of z as z approaches z0 equals f of w0. In other words, the limit of f of g of z as z approaches z0 equals f of the limit of g of z as z approaches z0. And so this property is really nice because it allows us to basically put the limit inside to the inner function rather than considering the limit of the entire composition as a whole. And so the last thing that we'll do in this video is prove this theorem. Okay, so surprisingly this proof is actually pretty simple. And so what we want to do is say, given epsilon greater than 0, we know that there is eta greater than 0 such that the modulus of w minus w naught being less than eta implies that the modulus of f of w minus f of w naught is less than epsilon. And the reason that this implication holds here is because we started off by assuming that f was continuous at w naught. And so by the definition of continuity, this condition has to hold. Great. So we derived this implication by the definition of continuity. And so we can actually derive another implication here. And so we can say for this eta, we know that there is delta greater than 0 such that the modulus of z minus z naught being between 0 and delta implies that the modulus of g of z minus w naught is less than eta. Now, why does this implication hold? Well, this implication holds by the definition of the limit, right? Because we started off by assuming that the limit of g of z as z approaches z naught is w naught. And so by the definition of the limit, this implication must hold. And so we're using eta here, but remember that eta is just some other positive real number. So there has to be a delta associated with this eta that makes this condition hold. Great. And so the last step of the proof is simply to string everything together. So we're going to say that this implies that 0 being less than the modulus of z minus z naught being less than delta implies that the modulus of g of z minus w naught is less than eta. And then by the top implication, this implies that the modulus of f of g of z minus f of w naught is less than epsilon, which is precisely what we were trying to show. So the proof of the theorem is complete. And that's it for this video.